Hello. Okay. Hi, everyone. Thanks a lot for coming. It's really nice to see you all here. So my name is Kishale. I'm a second-year grad student here in the astronomy department. So before we begin, I'll just announce the schedule for tonight. So we first have a public lecture, which is 30 minutes, a 30-minute lecture. Then we have a Q&A panel, which will be 90 minutes. So feel free to stick around to ask questions to a panel of specialists who will be here after the lecture. And right after the lecture, we'll also start with the telescope observing. So if you just go out, turn right, and go this way, on your right will be the north field, and that is where we have our telescope set up. Right, so it looks like a really nice evening tonight. So we'll probably see all of the targets that we want to. We have a bunch of interesting flyers for our other outreach events, and also some really cool astro stuff that you'll find on the table outside. I'd just like to remind everyone that food, drinks, and pets are not allowed in this auditorium, so thank you for abiding by that. And right, so if you need any kind of assistance, just find people with badges that look like this. So we are happy to help you anytime if you need anything. We have, so this is about monthly lectures. We have this once every month, and there is also Astronomy on Tap, which is where we give similar lectures at a local bar in Pasadena. So the handouts outside will give you details about those. Right, so I think we can, so the speaker for today is Professor Gregg Hallinan. So Gregg grew up in Ireland. He did his undergrad and PhD in Ireland before he came to UC Berkeley as a Jansky Fellow, and then he came to Caltech, where he is now Assistant Professor of Astronomy. And Gregg works on a wide variety of things that include mostly radio astronomy, things where he looks for hidden explosions that can be probed by radio observations. So I'll hand it over to Gregg.
Thank you very much. Hope you're all doing very well. It's amazing to see the house so packed, so it's great to see you all here. I'm going to talk about a phenomenon called fast radio bursts, mysterious flashes of radio waves from outer space. And I hope along the way I'm going to dispel some myths about these fast radio bursts, because if you Google fast radio bursts, about half of your hits are going to involve something like this, right? So I'm hoping that today we can get a bit of clarification about what these are and what these aren't, okay? They are mysterious, but they're not necessarily that mysterious. Okay, our story goes back about 50 years, way before the detection of fast radio bursts. I'm going to bring it back to another phenomenon. Here is a graduate student, Jocelyn Bell, also Irish, Northern Irish, and she was involved in a project in Cambridge to try to map varying sources on the sky. And she, at the time, we did not have big digital computers like we have today. You'd have reams and reams of charts, and you pull through the charts looking for the variability of your source on your chart. And what you saw was this pulsing source. Every 1.3 seconds, there would appear a pulse on her chart. Now, this is very mysterious. First, that's a very fast period. And at the time, there was no natural phenomena of which people were aware that could produce this kind of signal. In fact, all the astronomers involved at the time had emergency meetings for about a week where they tried to figure out how they were going to break it to the wider society that they maybe had found aliens. Because that was what their initial assumption was. They called it LGM1. That stood for Little Green Men 1. And that was a bit facetious, but there was a genuine chance that maybe indeed it was actually due to interstellar communications. That was a small chance, but a significant chance. Eventually realized that that wasn't what they were seeing, and the real clue came from seeing another signal very similar in a completely different direction, which really didn't suggest, the idea of two separate civilizations at opposite sides of the universe or galaxy pointing their telescopes towards Earth, sending a very similar signal was a bit unlikely. And eventually, theorists began to realize what was causing what we were actually seeing. After a few more years, it became apparent that what we were seeing was the remnant of the explosions of stars. Supernova. When stars explode, their cores collapse into a very dense state, very often called these are called neutron stars. They're very small and extremely dense. This is an example of a neutron star compared to the Chicago skyline, about 20 kilometers diameter, but weighs more than the sun. A teaspoon would weigh 1 billion tons. And as it's collapsing in, kind of like a ballerina pulling her arms in, spinning faster and faster, so does our neutron star spin faster and faster as the star collapses. And eventually, when it collapses all the way in, it spins as many as 100 times per second. And that's what actually we're seeing. We're seeing this very dense, compact object, and it has these jets of radiation that spin towards Earth, producing a pulse every rotation period. For that first pulsar, it was once every 1.3 seconds or so, which is kind of close to what we're seeing here. Some pulsars spin a lot faster. Here's another example showing a movie towards the most famous pulsar. This is the Crab pulsar in the middle of the Crab Nebula, and this thing is one of the fastest spinning young pulsars. It spins about 30 times a second, and it's actually visible with a small telescope to the naked eye, although your eye can't resolve the spinning. How do we find pulsars? Since that first discovery, more than 50 years ago, there are thousands more that have been found, and in fact, we know there are something like 100 million to 1 billion neutron stars in our galaxy. They only really emit these pulses when they're relatively young, or sometimes when they're much older, when they're spun up. How do we find them? We use very big telescopes, big dishes. This is the Green Bank telescope, and we can see for size the Statue of Liberty Washington Memorial Monument. You've got this enormous monolithic structure to detect the emission from pulsars. That's because pulsars produce very weak radiation. Bright by radio astronomy standards, but compared to your mobile phone or a microwave, very, very weak. If you combine all the energy from every pulsar that's ever hit Earth since the dawn of radio astronomy and put all that energy together, it would be less than one flap of a fly's wing. So a lot, really, really small amount of energy, and to collect a lot, to be able to detect that, you need a big, big bucket, which is what these telescopes are. And since that first discovery, we've found different classes of pulsars. We've found magnetars. These are really magnetic pulsars that have magnetic fields that are so strong they could tear apart the Earth if the Earth was close enough. You've got millisecond pulsars, one that spins like within a couple of milliseconds, do a full rotation. And even occasionally, some pulsars produce occasionally just a single pulse at a time. They're called rats. A very fundamental property of pulsars is that their pulses have a very particular behavior. Before I talk about the pulsar, I want to talk about the idea of how light is affected by passing through material. If you look at a straw through a glass, you can see the straw seems to have a break, or it seems to bend. That is because the water affects the propagation of light through the water, right? It bends the light. A similar kind of effect happens when we look at the radio emission from pulsars. Pulsars, the light from pulsars, the radio emission from pulsars is traveling from very great distances. And as it travels through our galaxy, in kind of a very similar way to how the water affects the image of this straw, the radio waves have a delay. And that delay, here I'm showing frequency versus time, that delay gets longer as you go to lower frequencies. So you have this kind of sweep, and we call that a dispersion sweep. Okay? The bigger the dispersion, the further away something typically is. Okay? And we often refer, when we talk about pulsars and fast radio bursts, we refer to a dispersion measure. And as a guide, in our own galaxy, a dispersion measure of 1 is about 100 light years. A dispersion measure of 10 is like 1,000 light years. Okay? And for the last 50 years, astronomers have been surveying the skies with these big giant telescopes looking for pulsars. Okay? And you know, there's been lots of important discoveries with pulsars. For example, there's been a binary pulsar that's been seen to orbit slowly and slowly closer in. And as it goes closer and closer in, it's been figured out that that's due to Einstein's theory of relativity. And there's a Nobel Prize awarded for that. And lots of other amazing discoveries. And one thing we can do with pulsars, because they have this dispersion as they are coming from further and further away, you can use that dispersion to go from a 2D image to a 3D image of our galaxy. So you actually can map based on how much dispersion you see, how far away pulsars might be, and what they're propagating through. So here we can see, for example, this is kind of a map of lots and lots of pulsars and their measured dispersion. And when we go into the middle of our galaxy, where you're looking through lots and lots of material, you see lots of dispersion. And when you're further out, you see a lot less dispersion. Okay? And these two bumps here are due to two satellites of the Milky Way, the small and large Magellanic Cloud. So when someone wants to find a pulsar, and the pulses are very, very short duration, milliseconds in duration, what an astronomer has to go and do is point their telescope somewhere and try to look for this dispersed sweep. The problem is you don't know what it's going to be. So what astronomers have to do is they have to put their data through a computer and shift and add it at a whole range of dispersion measures to try to find the right one that fits the data. And that used to be very difficult because it would take a lot of computers to do that, a lot of compute power. Which is why most of the time radio astronomers only ever really searched for dispersed pulses in our own galaxy. It just costs too much computational power to do otherwise. Now, it wasn't always the case. Sometimes adventurous people try to look beyond our galaxy. Here's an example of a search for pulses beyond our galaxy by Serafini and Joe Taylor. And basically, they used Arecibo and actually went to the trouble of looking for pulses beyond our galaxy. It was very computationally difficult, but very worthwhile. Serafini, who's a professor here, by the way, was a high school student at the time. And it was published in Nature. I promise you, it's not very often high school students publish in Nature. But Sterl is a bit of an exception that way. All right, so typically students, anyone would not really typically search outside a galaxy for pulses, but occasionally someone will go ahead and try. Here is Duncan Lorimer and Moira McLaughlin. And they actually were very interested in trying to look for pulses beyond our galaxy because they realized that computational power, Moore's law, had kind of caught up. Every couple of years, the computational power you have in your PC or your laptop or your iPad gets better and better and better. And they realized, well, you know what, we have enough power. Why don't we try to search for pulses beyond our galaxy a bit? And what they used was data from this telescope. This is called the Parkes telescope. It's quite a pretty telescope, I think. It's based in Australia, and it had been surveying the sky with this special 13-beam feed. Now, what does that mean? Each one of these little black holes is kind of like a pixel, and you can search for pulsars in that pixel. Okay? And what they had been doing, what they decided to do was look through old data that other groups had collected and try to reprocess it in their computers, looking for sweeps that were from further away than our galaxy. So the data they decided to look at came from the small and large Magellanic Cloud. And lo and behold, they found something. So here is the small Magellanic Cloud, and around about here, they saw a radio burst. It looked like this. It was extremely bright, and it wasn't a pulsing source. It was a single pulse. The single pulse was so bright, it saturated the receivers. Here, once again, you can see the sweep from high to low frequencies. It took about half a second to sweep through this entire band. When they placed it on the plot, which shows where all the pulsars are, they realized something. It was at a very high dispersion measure. It had passed through a lot more material than was in our galaxy in that direction. That meant it must have come from beyond our galaxy. This was a very exciting result, which they published in the journal Science in 2007. And why was it so exciting? They had found this one pulse, but it was incredibly bright. For a short period of time, it was brighter than most radio sources in the sky. It lasted only a couple of milliseconds, but during that time, it was incredibly bright. The thing is, nobody knows how far away it was, because we don't actually have a map of the gas very well beyond our galaxy. But crude estimates suggested that it was probably something like 10 million times more energetic In fact, that's incorrect. It was 10 billion times more energetic than a pulsar's pulse. It was incredibly energetic. When they did a calculation of what were the odds of finding one of these events, because their telescope had a very small field of view, they really found this astonishing result. There might be thousands of these bursts on the sky every single day. And the burst was actually called the Larmor burst. It was called the Larmor burst after Duncan Larmor, the guy I showed you earlier on, who made the discovery, and his wife Maura was also on the team. Okay? So, great discovery, very exciting, everything's great, except soon after there was trouble in paradise. Why was there trouble in paradise? Well, because astronomers began seeing other types of bursts with the same radio telescope. They began seeing bursts that looked kind of like these. And what was kind of alarming was these bursts had some of the properties that were the same as the Larmor burst. It's really great to have something so famous named after you, like the Larmor burst, until something goes wrong. Then it's a really bad thing. It's either or, it's binary. So this is an example of one of these new bursts that we're seeing. And these bursts also had a very kind of big sweep, very similar to what was seen for the Larmor burst. They had some other properties that were very different, though. They had this very kind of mottled behavior, or jagged behavior in frequency, and also they weren't just seen in one beam of the telescope. They were seen in every beam. All of the 13 beams of the telescope saw these mysterious bursts. Now, what that means is they must be out of focus. And that can only happen if they're really nearby the telescope. That means they were happening from Earth, not from space. And that was a big problem. Now, here's what the sweeping burst, I call that dispersion measure. If you try to calculate the dispersion measure for all these events, they were kind of clustered like this. And smack bang in the middle was this Larmor burst. Now, the Larmor burst did not show up in every beam. It only showed up in 3, which is kind of okay, because that means it was just very bright. These events that looked like the Larmor burst, but were not from space, were called Perytons, after the mythological creature that casts a human shadow, i.e. it's human-made interference on the telescope. So these were called Perytons. And I remember when this result came out, the Larmor burst. It was one of the most exciting results of the decade in radio astronomy. Everyone was super excited. And then the mood changed because of these events. And this debate went on for a couple of years. Are they real? We knew these were terrestrial, were from the Earth. But were the FRB, was the original Larmor burst, was that real? Was a big open question. And the debate raged on for a couple of years until 2013. And a new result came out. There were 4 new bursts. And all these 4 bursts all happened only in one beam of the telescope. So they looked like the Larmor burst. And people began to believe again that maybe these were real, that they were extragalactic. And like the Larmor burst, these were all occurring at some DM that suggested they were outside our galaxy. And in fact, they were coming from billions of light years away. They were incredibly energetic. There was a lot of debate about what to call them. They realized if there's lots and lots of these bursts, we can't call them all Larmor bursts. So there were different names that were suggested. One was fast radio transients, FARTs. That didn't catch on for obvious reasons. Eventually, someone said, let's call them FRBs, fast radio bursts. And some people call them FRBs, after the little toys, but mostly astronomers call them fast radio bursts. And how you name a fast radio burst is just FRB, year, month, day. And here were 4 bursts that were detected in 2011 and 2012 that really looked like they were astrophysical. But what about those mysterious perytons? Well, it turns out the perytons were very clustered in time. They only ever happened at a certain time of the day. Whereas the FRBs that looked real were kind of spread out all over. Their arrival time was kind of completely random. They could arrive at nighttime or at daytime. These perytons all seem to arrive at the same time. Around about 12 p.m. Does that kind of ring any bells, anybody, if something's kind of happening about 12 p.m.? Lunchtime, exactly, around about lunchtime. An astronomer began to think about what's happening at lunchtime. And it turns out, over in the visitor center, in the Parkes telescope, there was a microwave. And the microwave would not produce any interference if you left it alone, but if you were just a little bit too hungry and you opened the door a little bit early, inside in that microwave was a magnetron, and it was still spinning, slowing down. And that would produce a sweeping radio burst because it was slowing down. And that is where the mysterious perytons are coming from. And there's a bunch of papers. Actually, one of the papers was from Jonathan Koch, who actually is here at Caltech now. Happily, the alarm burst was somewhere over here. So once again, everyone began to believe these are actually real. So now we can ask the question, what are they? What actually are they? Before we get on to what are they, let's talk about what they're not. Once again, I've already mentioned, if you go online and put in FRBs, you'll be hit with images kind of like this. And there's lots of reasons why FRBs have somehow become really associated with ET. And I'm going to go through these in turn. One is because radio telescopes, like the ones that detect FRBs, are searching for pulsing radio signals that might look like FRBs. And in fact, telescopes that are involved in this include the Green Bank telescope and the Parkes telescope. And it has really become a very concerted effort in the last few years, because $100 million have been invested in the last year by Yuri Milner in this breakthrough illicit initiative to try to search for radio waves from SETI, from extraterrestrial intelligence. And you know, the image of radio telescopes looking for alien signals really are embedded in our consciousness for many reasons. One, for example, the movie Contact. We see Jodie Foster with her headphones listening for aliens, which, by the way, radio astronomers do not do. But anyways, that was part of the movie. Another reason why I think FRBs are always associated with aliens is because we want to believe, right? Lots of people really, the idea of finding extraterrestrial intelligence is one of the grandstanding, challenges for humanity, finding life like ourselves. So, when we hear about mysterious signals from space, it's compelling to think maybe they are aliens. And there's a third reason, I think, why you tend to have this association between FRBs and aliens, is because very often the media will kind of present that kind of idea that maybe they're due to aliens, because aliens sells. If you have alien in your headline, usually you get clicks. And I experienced this myself about a year and a half ago. We built a new telescope, nothing to do with FRBs or aliens. It was just to image the entire sky every day, looking for radio emission from planets and from other sources. And here's an example of the entire sky at radio passing overhead. So we were very excited to buy our new telescope. This, by the way, is a pulsar pulsing over here. So we said, let's do a press release. So we did a press release, and we wrote a press release about how this is an important telescope for looking for radio emission from stars and planets. And here's an example of one of the headlines that showed up about a day later. Is this our best hope for finding alien life? However, radio telescope array can now scan the entire sky instantly in the Daily Mail. And that's kind of part of the problem. We are pretty sure that they are not associated with alien technology or life. You can never be 100% sure, because science is never 100% sure. We look at the evidence, we examine it, we present hypotheses, and the hypotheses that we look at and present for FRBs do not favor that concept. So what are they, and why do we care? Well, there are 34 FRBs detected to date that we know of, and there are about 41 theories. So there are more theories than there are FRBs. Okay? So the answer is we don't know. But there are lots of very good theories, we just don't know the exact answer. Why do we care? Well, there are two main reasons we care. One, something is happening that we don't understand. Okay? There's clearly something very energetic involving neutron stars or black holes or both that we haven't figured out yet. There are questions we can ask and learn about by understanding where in the stellar life cycle you get objects that produce radio bursts that can be detected halfway across the universe. So that's the first reason. The second reason is, I already mentioned that when an FRB propagates through material, the plasma in our universe changes it. It slows. You have this dispersion sweep. It also imprints the signature of the magnetic field between our galaxies on that burst. So we can use these FRBs to map the universe, map the gas between the universe. We actually know that there's a lot of the baryonic mass, not dark matter, this is baryonic mass. We don't know where it is. It's missing. It's not in our galaxies. We think it's in between our galaxies, but we don't know for certain. We can use FRBs, measure their sweep to figure out what lies between the galaxies, and that's very important. So what we do know, we now have established, and I'll explain that in the next couple of slides, that they are extragalactic. We know they're very energetic, and they likely involve some really compact object doing something very funky we don't know about yet. And that's really the quest. So why haven't we learned more about fast radio bursts? The big problem we have is that it's very difficult to pinpoint where an FRB comes from. Why is that? Well, the resolution of any instrument that's detecting electromagnetic radiation depends on two things: the wavelength of the light, and also the size of the instrument. We have, our eyeballs are receptacles. We detect optical light, and we have a very, very small opening. Radio waves are also a form of light. They happen to be much larger wavelength. So much so that even though the telescopes are much, much, much larger than the human eye, the human eye has a better spatial resolution than this telescope. So when we detect a fast radio burst, we know what happens like somewhere over here, but we can't pinpoint which galaxy in the far distant universe it came from. How do we solve that problem? We can't build a dish, that's as big as Pasadena, for example, right? It was mechanically impossible. It would cost too much money. What you can do, however, is connect lots and lots of dishes together. It's called an interferometer. And you can use that across a very big distance to look for events. However, turns out that's really, really hard. Why is it really hard? Because now you've got to search through all the signals of every telescope combined. And I said computers have gotten a lot better. They're not quite that good yet. Okay? But if we can figure out how to do this, we will be able to find out whereabouts FRBs come from. And we have managed to do it for one burst. Here is a very famous repeater, FRB 121102, the repeater. Why is it so important? Because it wasn't just one burst. Astronomers came back a month later and found another burst, and another one. This one keeps producing these FRBs. You can only imagine how the press reacted to that one. You're seeing it's repeating from the same direction, it has to be aliens. So when astronomers, because they knew it was repeating, they could then point the VLA, which is an interferometer, towards this source, collect a small amount of data, and finally localize where in the universe it comes from. So here we have an image, and we zoom in. This small little smudge here is the galaxy, the host galaxy of that fast radio burst. That little galaxy is 2,000 million light years away, 2 billion light years away. It took 2 billion years for that fast radio burst to get here. There's so much we've learned about fast radio bursts from just this one event. It's been on the cover of Nature twice because it's been so powerful. It's only one event, and we got lucky because it repeats. We need a new kind of telescope that can actually detect these FRBs and localize them all the time. The problem is you have to process a lot of data, like 10 petabytes, 10,000 terabytes a day. And that's not easy. But that's what we're trying to do here at Caltech. We're building, instead of building lots of big dishes, the problem with big dishes is they've got a very small field of view. We're building small dishes, lots of small ones, only a few meters in diameter, to image a very large field of view. And this is called the Deep Synoptic Array, and we're building it right now to try to localize fast radio bursts. It's out in the Owens Valley, about 4.5 hours north of here, at the Owens Valley Radio Observatory, which is Caltech's radio observatory. And what we're going to do is combine hundreds of cheap dishes. Instead of spending $100 million on a big giant dish, we spend $10,000 each on lots of small ones, and then stuff a massive supercomputer at the back to crunch all the numbers and give us our FRBs. Okay? Here, and unlike those big dishes that take a decade to build, these arrive in boxes and crates, and our staff assemble them. And we build all our electronics right here at Caltech. Stick them on, and so far we built 10 of our DSA dishes. And these are so low cost compared to the big dishes you normally associate with radio astronomy. For example, that's a cake tin that we're using as our feed. We're trying to build a low cost telescope with a really powerful computer. And our goal, within about a year from now, is to build not just 10, but 110. We're going to have 95 dishes on this T here, and then we're going to have 15 more dotted across about 1.5 miles of the valley, coming online we hope about a year and a half from now, crunching 10 petabytes of data per day, and it's going to find a new FRB and localize it to its host galaxy about every 3 days. So it's going to change, we hope, and revolutionize the field of fast radio bursts. Okay, thank you very much.
Okay, we have time for a few questions.
There's one here, and one here. You pick.
Yep. Did you have a question? Yeah.
Where are these new dishes in relation to the existing dishes that overall?
So, if I can go back up, I think I have let's see. All right, so just about a little bit south of here, you have two big 90-foot dishes that were built in the 1950s. You have the 40 meter, which is right about here, and then you have a VLB antenna. So they're all running about due south. This T-shaped structure here was the site of the millimeter array, the MMA, in the 1970s, 1980s, and early 90s. And we just use the same infrastructure. Once again, trying to cut corners, do it for low cost. We can use all the optical fiber, all the power infrastructure that's already there, by just using the same material used before. How many dishes we have so far? Right now, we have 10 small dishes. Right, these guys right here are not part of the DSA. We're going to clear those ones out of there very soon and build 95 more up and down here. So we've got 10 so far, and we're going to have 95 more coming in right there.
They have to be optically connected together, like with.
So how we transport our signal, we convert the RF signal from a low noise amplifier into an optical fiber and transport the optical fiber signal underground back to a central building over here a little bit, and we plug them all together and convert that optical fiber signal back into a radio frequency signal on a cable, and then we digitize it. We sample that signal, and we have to sample that signal about 500 million times per second on each of 110 dishes, so it's a lot of data.
So you're sort of simulating the interferometry then?
So then we look for the bursts by combining all the signals together, and we do the interferometry at the end when we find a burst. So we have it's a bit more complex than that. We do beamforming to find the burst, and then we do interferometry to localize at the end. So I mentioned the problem at radio wavelengths is that you need a big dish to localize, right? And instead of building one big dish, we use lots of small ones to synthesize a larger aperture. If we don't have those antennas out to long distances, we won't be able to pinpoint the galaxy well enough to find out where it's coming from. So this is not good enough. We have to go out further to give ourselves a much sharper image of the sky at radio wavelengths. Yep. So there are some that have very different properties, absolutely. For example, one burst that was discovered by a postdoc here, Vikram Ravi, was incredibly bright, the brightest ever seen at the time. And he could use that then to measure the magnetic field between here and the distant galaxy where the burst came from, and it was very weak. So that was one of the first constraints on the magnetic field in between galaxies. And there are some other things that are a little bit different. We know that fast radio bursts don't appear at low frequencies, only at higher frequencies. There's lots of other subtle structures. Some have what we call scatter. They get scatter broadened. They last longer than they should last. Lots of other little effects like that happen. At the front. It's a good question. You can do that. There is an array called the Very Long Baseline Array with 10 dishes all over the US, including one actually right over here. Oh, that's it right there. That dish right here. That's it there. Yeah. That's one of the 10 dishes that's spread all over the US. One in Hawaii, one in St. Croix, and that can pinpoint better than the Hubble Space Telescope. For now, that's all we need to pinpoint to a small host galaxy. Maybe in the future we might try your plan and go a bit further out. All right?
Is it possible to actually fly it?
It's definitely possible, but not a good idea. It's pretty high up. It's a lot smaller than a big dish, but it's out bigger than a small dish. That makes sense? No, the dishes have a height about the same as the ceiling here, so it's a little bit dangerous to climb up them. Yeah.
I noticed that on the pole stars, the poles have to be aligned to us to orbit.
That's right. You have to have the lighthouse swing by and beam towards you. So some we don't see at all because they don't beam towards us. Yeah.
So, okay. Yeah, we'll have time for more questions after a few announcements.
Yeah.
Go ahead. Yeah.
Talk a little bit more about the computer system, the networking. Where is the computer system going to be?
Sure.
Do you have a high-speed connection to that computer?
Yes. Yeah. Sure.
Staff to support the
So everything comes along through here into this building, which is the Mayor building. So we bring all the optical fiber back through here, and then you have to sample each one of these signals with what we call an analog digital converter, an ADC. That samples at 500 million times per second, times 110 dishes, times 2 polarizations. That's a lot of data. Then we stuff it all into a type of electronics called FPGAs, and they're really good for doing the first step of finding the FRBs. And we also have so what's really nice, those of you that have gaming systems or computers at home, they have a piece of electronics called a graphics processor unit, a GPU. Okay, there's been billions of dollars spent on making those really good. Turns out they're really good at finding FRBs. So we can take all that money and investment and put a load of these GPUs in our building right here and search for the bursts by using those, because they're really well optimized to try and find. Unlike your laptop can do, you can play, you can use it for Facebook and you can use it for lots of different things. It's very versatile, but it's not very good at doing any one particular thing. GPUs are very good at finding FRBs.
NVIDIA CUDA?
Yeah, we use NVIDIA CUDA. That's what we're using as a framework for the GPUs. Yeah.
All right, thank you all for coming. We thought that since we had so many great questions afterwards, that you guys could all just ask us the questions and that everybody could hear the answers afterwards. So ask away. Oh, yes, we should introduce ourselves. My name's Dylan. I'm one of Gregg's PhD students, and I work on radio explosions, although ones that last for a much longer time than the fast radio bursts that he was talking about. Fast radio bursts last for about a millisecond. The kind of bursts that I look at last for like years.
Right, so I've already introduced myself, but I'm also a second-year grad student, and I work also on explosions, but not quite the radio explosions. I work more in the optical, where we look for exotic explosions that go off in the night sky by using small telescopes that Caltech operates and owns. So.
I'm Catherine. I'm a first-year grad student, and I'm looking for a repeat burst from that repeating fast radio burst, but I'm looking at a higher frequency than has been looked at before. So it's essentially looking at bluer radio waves that we've seen.
Yeah, thank you.
Yeah.
I came across a term in a science documentary
So just a ordinary nova, or is there another prefix?
Something that implodes on itself. I was wondering if you know a little bit more about that.
So there is one kind of supernova that we think instantaneously has a prompt collapse of the black hole and doesn't give you the same bounce of material that gives you a supernova. I'm thinking that's what you're referring to. So there's examples of a Hubble Space Telescope seeing in other galaxies very, very, very bright blue stars, and then they come back later on and they're gone. And that usually means they've exploded, but there was no supernova. And the expectation is that you expect that for certain scenarios for a very massive star explosion, and that these are examples of these on novas. Yeah, so it's just basically because they don't go through the same chain reaction of nuclear material creation that you have in the supernova process. They just have a prompt collapse. They're extremely energetic events, but we don't see them for that reason.
Yes. Let me bring you the microphone.
You mentioned there were 41 theories for the fast radio burst, and you mentioned the neutron star. I'm wondering, can you look at like our nearest galaxy or even neutron stars in our galaxy to see if it shows the same patterns, or if some of the other theories like are black holes and you're looking at things being ejected from black holes? Can you purposely go look for it?
That's a very good question. Certainly, in the case of neutron stars, we know of lots of holes in our galaxy. And you ask the question, do any of the neutron stars in our galaxy behave or produce fast radio bursts? To the best of our knowledge, we haven't found one from anything in our own galaxy. And we haven't had enough coverage of other nearby galaxies to say if they're produced regularly by other galaxies. Caltech mentioned a project to try and look at one galaxy that we know has one. And in terms, we think that may mean that this neutron star is unlike anything in our galaxy. And that can be easily explained by the fact that maybe it's a very young neutron star. You know, a supernova, we're not aware of any supernova having happened for many, many decades to maybe even a century or beyond in our galaxy. Maybe what you need for an FRB is just, you know, a year-old neutron star that's, you know, spinning like crazy. Or maybe it involves having neutron stars very close into the supermassive black holes in the middle of galaxies. That's what I actually believe the model is, but we don't know that yet. And there's like dozens more. Some people one model was that maybe it's stars flaring, which was wrong. One model was that maybe it's the sails from like giant extraterrestrial spacecraft. I also think that's probably wrong. You know, it's just like there's endless theories. But we are honing in on certain things about them. Like the galaxy that we see that one event from repeating, it's a very special little galaxy. It's a very small galaxy, and it's producing lots and lots of new stars. And there's a little small radio source that doesn't go away, sitting right under the location where the bursts are coming from. And all those clues are beginning to build a picture.
Yes? Yeah, in the back?
Related to the antennas, so the 40 meter, you're going through like 1.2 and 1.5 gigahertz mostly. Is there a reason why you don't go above and beyond, below? Like, for example, like we use HF and VHF. So if you're trying to find extraterrestrials, wouldn't they probably use 100,000 watt FM, HF transmitters? And when you want to look at low frequencies, because that's more likely what they'd be using on their planet because it propagates better for communications.
Well, so we do look at different frequencies and for different reasons. And the reason a lot of radio telescopes look at like you said, the 1 to 5 gigahertz is that is what gets through our atmosphere the best. At much lower frequencies, the ionosphere gets in the way, and at much higher frequencies, the water vapor gets in the way. And you mentioned lower frequencies for communications, and that works great on Earth because we can actually bounce it off the ionosphere. But if you want to look at something that gets through the ionosphere, you want to look at higher frequencies. And people have looked for fast radio bursts at low frequencies and haven't gotten them yet.
I think usually above 100 megahertz, it will escape our atmosphere pretty easily. Like
10 megahertz.
Yeah, real low frequency. So I'm thinking pretty low relative to gigahertz, like VHF is still pretty low. But you don't look at that.
Part of the issue is that we can't build. We're still in the process of building telescopes that get as sensitive at those low frequencies. We can't. At gigahertz we can cool cryogenically the receiver, whereas at low frequencies everything is really hot. So we have to build a lot more collecting area. That's part of and the reasons that Catherine mentioned also. In the future we will, but yeah, it may be though like the very first SETI searches that I'm aware of are there was a project about a century ago that involved building huge piles of hay in a field in France in a big circle and writing letters and then setting it on fire, and the hope was that Martians would see it because that's the only form of communication that we were aware of at the time. So maybe we're just very primitive. We're a very young civilization, and we could be doing the equivalent of lighting hay on fire in a field from the perspective of alien civilizations.
Yeah.
Is there any plan to apply the interferometry principle to a constellation of telescopes?
Sorry, to apply it to what?
To apply the interferometry principle to a constellation of telescopes in space?
Yes.
Is there
Yes.
a plan to do that?
I don't know its current state, but well, there's at least one telescope that does do that as part of very long baseline interferometry.
Is there any plan for the future to launch a constellation of space telescope to do that?
Yes, but I don't think it's an immediate plan.
Yeah, so I'm involved with two big projects. One is to build, like 1,000 small satellites, like a swarm, and the other is to build a big dish on the far side of the moon. There are two concepts we're looking at. They go to the far side of the moon just to get away from the noise from Earth, right? You can just use the Earth as a big shield. If you're trying to find aliens and you've got the nearest aliens is like next door, you want to get rid of the noise, so you point it on the far side of the moon away. And one really idea that I really like is the idea of taking a giant crater that was created by an impact that was almost exactly orthogonal, and then getting a little rover and putting wire across that crater, and suddenly you have a giant radio telescope. And that's what it'll look at the Death Star, but it'll be a really powerful radio telescope.
Yeah, and I also wanted to point out that there already exists one space telescope that connects to telescopes on the Earth. It's called Radio Astron, and it's incredibly technically challenging to get it to work, but they can get incredible resolutions, like I think micro-arcsecond sort of resolutions. Yeah, go ahead.
You mentioned the large telescope, like 40 meters. What kind of equivalent in decibels of gain does it have? I'm a ham guy. I'm just curious. What is this?
So all three of these students had that exact question as part of their homework in a class that I taught. So I'm really looking forward to them explaining the answer. This is going to be really good. Oh, good question.
But I can calculate this, but I can't just recite the answer. So the larger the aperture of the telescope, the smaller the beam size it will have. And we talk about a beam for a radio telescope because you could imagine a telescope that is collecting light from some part of the sky and telling you all the information that was in that light. Or imagine turning it around as a transmitter and you shine a flashlight on some part of the sky. And the cool thing about radio telescopes that's a useful trick for calculating things is that in a lot of ways they work the same either direction. And so the part of the sky that you're collecting light from is the same part of the sky that you would shine a light on if you instead turned on a transmitter in that same dish. And so when he's talking about the gain, he's talking about how much your dish sort of amplifies the signal to give you a brighter signal than you would otherwise see on the sky. And the wider the dish, the more focused the light is into a smaller, so you're sensitive to a smaller part of the sky, but you can see fainter and fainter things because it's like you're shining a brighter flashlight beam. And I think it would be beyond the scope of this to have us get out the whiteboards and do that calculation right now, but basically it depends on the wavelength, it depends on the size of the dish, and I think that's probably enough of an answer for this.
Yeah, a simple way to figure out that for a big dish is its field of view is just lambda over d, right? So you said a 40 meter. So if we're talking about doing 21 centimeters, okay? 21 centimeters over 40 meters is a couple of hundred radians. Sorry, 1/200 radians. So it ends up being something like about a degree or so across. A little bit less than that. Yep, which means it's a simple calculation then. We know there's 41,253 degrees in the sky. So your gain is just 41,253. So about between a few times 10 to the 4 is your gain.
So 1,000 times gain, so 30 dBi. Suppose if I took a radiator, how much gain does it have over that in the radio world?
Exactly that, about 41,000 in terms of relative to an isotropic emitter. So 40. So that's.
So it's actually not that much as I thought it would be.
Well, yeah, you usually have lots of dishes together. So like the biggest dishes, biggest telescopes, and it depends on frequency. You go to higher frequencies, you can get like 10 to the 7 gain if you want, which is the high end.
Yes.
So that's, sorry, 70 dB gain.
It's the same thing.
Yeah.
Base 10 is long.
Exactly, yeah. Just to make sure, yeah, dB.
70 dB is the same as 10.
Yeah, just make sure I was saying in dB in case.
Yeah.
Are any of these bursts that are outside of our galaxy affected by gravitational lensing?
It's possible.
It's a great question.
And it's actually statistically likely that the brightest of anything that you observe could have been lensed.
It's a great answer.
The question was if any of the fast radio bursts that we've detected have been gravitationally lensed. And so for that to happen, you would need a large mass, like another galaxy in between, and then light bends around that galaxy, and the burst gets, it's like putting a magnifying glass in front of it. And since it's so hard to pinpoint where these bursts are coming from, we're not even in a position to find its host galaxy, let alone everything it could have passed through. And so we can't say this burst was lensed, but you can actually do a statistical argument that says probably some of in anything you look at, the brightest examples it's very probable that one of them was lensed. Yes?
So given the distance that these signals are traveling, could they theoretically have been gamma ray bursts that have been redshifted to a radio spectrum? Because they're coming from so far away. Is that a possibility?
I don't think that would be possible.
So yeah, I'll repeat that question. So the question is so we know of similar kinds of mysterious explosions called gamma ray bursts. And the question is whether gamma ray bursts, if you redshift them enough, so it turns out that the further you look into the universe, light gets redshifted, in the sense that if you look at light that is being emitted here and you look at it somewhere else, then the light that you see appears longer in wavelength, and that's just a consequence of the expansion of the universe. So the question is it possible that a gamma ray burst, which is very strong in gamma rays, can that be redshifted enough to look like a fast radio burst for all the way, in the sense that something is getting redshifted all the way from gamma rays, which is very high frequencies, to radio waves, which is low frequencies. So I think the answer to that is no. And the reason being that the redshift, the distance you would need to redshift a gamma ray burst from gamma ray frequencies to radio frequencies is incredibly large, in the sense that at that point you're looking at a time in the universe where basically nothing existed. So we know that the universe has a certain history where it formed stars, and today, we roughly know when most of the stars were formed, when the stars first started forming, and what it is today. So if you take that history and ask the question, can a gamma ray burst be redshifted to radio frequencies? It turns out that the age of the universe that you're looking at, there's no way any stars could have formed by then. So I think that's the simple answer to that. I'm not sure if there is.
That is a very good answer. There's two other aspects to it. Is that the gamma rays are not bright enough. The radio emission is coherent. The gamma rays are not coherent. And the third thing as well is we know how many gamma ray bursts on average happen in the universe per day. And it's way too small to account for fast radio bursts. There are a lot more radio bursts on the sky every day than there are gamma ray bursts, both those we can see and those we can't see. So gamma ray bursts can't be accounting, just by virtue of there's not enough in the universe per day to give us fast radio bursts.
Yeah. Just to add on to that a little bit, if you were to redshift a gamma ray into a radio wave, it would have to be located around when the age of the universe was like less than a second old. And so there were no stars, certainly. There weren't even, I'm pretty sure, atoms at that point. Yeah. Mm-hmm.
Someone was asking me about using interferometry in telescopes, right? Satellites, right? And so I was thinking about the LISA, or what was it, the big something observer. So those are not for radio astronomy, but for gravity astronomy. So for some reason, they're using interferometry for gravity waves. I guess because it's such a large phase that you're taking out, right? But is there any other reason why that comes to mind right away rather than radio astronomy, doing radio astronomy with interferometry and satellites in space?
Yeah, so I guess the word interferometry, so first of all, the question was, and correct me if there's anything more to your question, the question was, there are many different kinds of interferometers, and one of the more famous examples of interferometers are instruments that are used to detect gravitational waves, not radio waves, such as LIGO and LISA. And LISA is a planned space mission which is going to involve 3 satellites that are in a triangle, and they'll be able to detect gravitational waves produced by supermassive black holes from merging galaxies. And so, is there any relation between that kind of interferometry and radio interferometry? And in a very broad sense, yes, it does involve taking advantage of the fact that any kind of light, in the case of LISA, it's lasers, but in the case of radio interferometers, it's just radio waves that are coming from space. The fact that light, when you combine the waves, has very specific interference patterns, and you can get a lot of information out of that interference. But past that, there's tons of different kinds of interferometers, and the actual way that this interferometry works between radio interferometry and gravitational wave interferometry is very different. So in gravitational wave interferometry, you're looking for slight distortions in the amplitude of your lasers because the path length has changed. And in radio interferometry, you're looking for somewhat the same thing, but it's because, not because the intrinsic path length between your 2 detectors has changed, but it's because the angle of the source on the sky is slightly different.
Okay, so the other part of the question is, why are there famous examples of interferometry for gravity wave astronomy, but I haven't really heard of it using interferometry so much for radio astronomy with satellites in space?
Yeah, so the question is, why are there famous examples of gravitational wave interferometry and not so much radio interferometry? I would say there are famous examples of radio interferometers.
Not in space.
Oh, not in space,
That was
certainly, yes. Definitely not in space.
Yeah, and that's a very good
Yeah.
point.
Why? It's just because it's
We don't need to go to space. The main reason is we don't need to go to space for most of the radio interferometry. It will work almost as well on the ground as it will work in space. It's different for the gravitational wave. So LISA is measuring the very distortion of space-time, right? It can measure the changing, light has the same speed in any reference frame. And, if you're measuring the speed of light, you're measuring if the space itself is distorting around the light. And that's what you do with gravitational wave observatories on the ground in space. The problem is, if you're walking on the ground and you have like LISA 100 miles away, it will detect you're walking on the ground here. So getting away from other sources of vibration makes it much more sensitive. So it's a prerequisite for LISA to do what it's trying to do. It's not a prerequisite to do a radio telescope on the ground. So if it costs, if it costs 10 million to build a telescope on the ground, it costs something like 10 to 100 billion to build it in space. So you only have to go to space if you really want to. Need to, really, I think.
You can more easily sort out the interference from Earth.
That's right. You're isolated from the vibrations caused by everything around you on Earth if you're in space.
Yeah?
So for the bonus value sites, what was the motivation for clustering the radio telescopes in the way that you did on the map? Was it convenience because of roads, or was there more like we need this geometry to detect a certain region of the sky?
I'm happy to answer that, but given the also this class can also
Okay, so when you have an interferometer, each baseline, so each pair of telescopes gives you spatial information on the same size scale as the resolution of a single dish telescope that's as wide as the telescopes are separated. And so I guess that was sort of a long way of saying that every pair of telescopes is giving you information on a particular size scale on the sky. And so you want to arrange them. If you went and arranged all of your telescopes in a grid, then you have many pairs that are exactly the same distance apart as some other pair, and so they're sort of redundant. And so you want to arrange it in a way to give you, instead of thinking of how you're arranging individual telescopes, you want to think about what all your different pairs of telescopes are.
You're looking basically with a cracked telescope. You've got lots of holes.
Even optical telescopes, when you look at the Hubble Space Telescope image, and you see every star has like these 4 spokes, right? Every star, has these like 4 spokes in every Hubble Space Telescope image. That's just because there are 4 legs that are blocking some of the mirror. So when you have holes that are blocking your mirror, or when you've only got some of your collecting area, that will distort what you're seeing. And like Catherine says, we can pick where we put our bits of our mirror of our giant telescope to try to minimize some of those problems. Yeah, we can kind of optimize our cracked mirror, basically.
It's a funny one, but I remember reading this article. I'm not sure if it's real or not, but supposedly we're picking up our own station, our own broadcast from like the 50s, reflecting off somewhere about 25 light years away, and then it's now 50 years later, and now we're picking up video of like old TV broadcasts. Is that just a made-up story, or is that possible? Reflecting off something?
It's definitely not possible. What is happening is that our broadcasts are hitting other stars now. So depending how far away the star is, depends what they can tune into. We can pick up things that reflect off the moon. So we can point a telescope to the moon and tune into radio stations. And in fact, there's a professor here who's an avid ham radio enthusiast. Sri Kulkarni was observing with the biggest dish on the planet at the time, Arecibo, And he was an avid ham enthusiast and decides to do a moon bounce and basically flood every ham enthusiast across the entire US with his moon bounce. So you can detect it, but not from that distance, because the attenuation goes as the fourth power of the distance. So it's just far, far too weak. But civilizations that are that distance away will, if you're 50 years away, light years away, then you're tuning into 1968, just after the Summer of Love, Vietnam War. That's what they'd be picking up if they were watching the radio waves then. Yeah.
But we used to have 500,000 watt transmitters in the 20s, 30s. The idea was, but that's still, you're saying it's so insignificant compared to, say, a pulsar or something super crazy. This is nothing.
That's right.
Small. It's there's no hope of taking that.
Exactly. It's impossible to do.
So if we do get our television signals coming back, then it's aliens.
Exactly. That is correct. That is correct. Then someone's picking it up and just broadcasting it back. And there's a big debate about whether or not we should broadcast. It becomes almost a philosophical question about should we let ourselves know that we're here. And there have been broadcasts towards a globular cluster, for example, a very famous one. It was hotly debated between academics whether that was an unethical thing to do or not, because we don't know if the societies that we broadcast to are friendly or otherwise. But you can certainly broadcast. The biggest dishes on the Earth are Arecibo and the FAST telescope in China. You can put two of those either side of our galaxy, and they can communicate with each other. It would just take about 100,000 years for one signal to go one way and then back. So the delay, when you're talking to somebody and it's a bit of a phone delay, imagine like a 200,000 year delay. Not very tenable.
So, as Greg said, just an interesting trivia. So the globular cluster that we are looking at today with the telescope is the same globular cluster at which we had sent a radio signal a few years ago. So in case you want to wave hi to your alien friends, please go out and have a look at the telescope.
Yep. So they did send a radio wave towards the globular cluster. What did they send, and how long did it take to get there?
So I don't quite remember what they sent. Do you remember what they sent? It's
sequences like prime numbers, things that would be obviously due to man-made transmissions on a very narrow band signal.
Right, and it would take at least a few thousand years for the signal to get there, because these are typically a few thousand light years away. So, there's still some time before they get to know we exist, unless there's something in between them and us, and some other system just picks it up.
Because globular clusters don't, we think, have many planets anyways, for dynamical reasons.
Just to follow up, then why did they decide to beam it there? What was the thinking?
Lack of knowledge. At the time, it was a place where you could beam to a whole lot of stars all at once. But we've since figured out that globular clusters are probably not a good place to look for planets, because the stars are all so closely packed in that it's much easier for planets to get out.
What year was that?
Late 70s, wasn't it, I think? Yeah.
So if you're against it, then
Yeah. It is a major ongoing thing, let it be known that we're here. Yes. Right. That's the analogy that's been used by people like Stephen Hawking, actually, that any contact with an advanced civilization in human history has ended very badly for the less advanced civilization, which would be us, probably.
Yes.
Your limiting factor of the computer data, is it just like analyzing all the terabytes, or is it something else?
It's exactly that. It's the amount of data that you have to sift through. You've got to do all the shift and adds to try and find the right dispersion, and do all those simultaneously on lots of telescopes simultaneously. It's just really, really, really computationally difficult. You're pushing something like a few percent of the U.S. internet traffic, equivalent to that. The entire U.S. internet traffic. You're pushing a few percent of that through that one building on the site there. Something like 5% equivalent, and you're pushing all that data through that one building and sifting through it for those bursts. It's a very computationally difficult problem.
What's the current analyzing per second?
How much data per second? You mean? Well, the raw data rate is 110 dishes, and each dish has 2 polarizations. That's 220 dishes. When it's finished, and then you're analyzing 500 mega samples. That's 500 million samples per second. Each sample would be, let's say, 8 bits. So let's say that's a byte. That's 200 times 500 million. So that's 100 million bytes per second. Is that right? Or is it 1,000? No, it's 1,000. Is that right? It's 200 times 5. 500. Yeah, so it's yeah, so it's 100 gigasamples per 100 gigabytes per second. Yeah. I already have a telescope that does more than that. The Ultra does more than that, actually. More than the DSA. Yeah. It's coming in, and it's been written into RAM buffers, so we can't write it to disk because you just basically got this fire hose coming at you, and people like Catherine are actually solving the problem. Catherine's very familiar with the digital hardware, much better than I am, that you need to develop to deal with that in real time. So people like Catherine are just basically like writing the algorithms, handle that many bytes, per second. So you should ask her how you do it. How possible, to be honest.
So for the first steps of processing, we use field programmable gate arrays, which are so when you compile a program on a computer, the compiler finds the best way to do that program on the computer you have, and it takes into account what's available on that particular computer. So you can imagine it'd be really good if you could have a computer that had its resources be just the right thing for the thing you want to do. And so you could make a custom circuit, and then it would have one job, and it would be the best possible way of doing that one job. But you can't ever decide to tweak it a little bit, make it do something different. And so field programmable gate arrays are really cool because they're a compromise. They act like hardware that you've built to just have that one job, but you can reprogram them and reconfigure them. So there's sort of like a fabric of logic circuits that you arrange how the logic circuits connect, and it then can do one thing very fast because it acts like built-in hardware rather than a computer that is good at doing many things.
The data array that normally would be built in software, but you're building a hardware version of the data array?
You're sort of writing out the way you would do it in hardware circuits. So you can build a circuit that adds something and a circuit that multiplies, and everything we're doing is different forms of adding and multiplying and some logic statements. Everything that you do on a computer can be broken down into that. And so technically anything you did on a computer, you could, with the right number of ands and ors and multiplies and stuff, you could build any of that in a physical circuit. That would just be fixed. The wires would be connected in place, and it would do that one thing. And what an FPGA does is it mimics that, but it can rearrange itself.
We're always buying stuff online from China, but not this particular problem. Only that's another this one.
Yeah, so and I thought I heard before when you were answering questions, you're analyzing a bunch of data, and most of the time you're probably just going to throw that data away. Like you're going to erase the RAM. You're not really saving much.
That's right. You buffer it. You put it into so we can store data and manipulate data very well in RAM. or equivalent to RAM, what you have on your computer. So you got RAM, and you got your hard drive, and you got your CPU. We can buy lots and lots and lots of RAM, and we can write and read to that extremely quickly, but we can't read and write to disk very quickly. So we tend to do all our operations either directly in physical hardware, like the initial steps we all do in physical hardware that Catherine described, FPGAs. Then we actually bring it into computers that have these great, just these graphics processing units, and we use those. They're custom designed for certain problems, like Catherine described. They've got logic that's very good at particular, multiplication of numbers particularly. They're very good at that, and we can optimize. We can write our once the numbers have been crunched or processed slightly by the FPGA, we stream them into this computer, and then we start doing what we call de-dispersion trials. So the data comes in, and we don't know what's the actual sweep, right? If you want to maximize the signal to noise, you want to add it all up to be one light curve, one bump. But you've got thousands of channels, and it could have this characteristic sweep because of passing through all that material on the way to coming to Earth. So what we do is we define a whole lot of trials, and we look for a bump. And when we get the right, when we find a bump at the right trial, that's our signal. But that's all a very computationally complex, expensive rather, process. So we're doing all that, and meanwhile, we're writing all the raw voltages of every antenna to a RAM, to buffer. And when we find something, we then say, stop, everyone freeze, and write everything to disk then. Just that small chunk of data, the few milliseconds where we have a detection. Then we write everything to data, to disk, to hard drive. And we can do whatever we want after that then. Not that much data that we store, no, not really. I mean, still like terabytes, but like in our world, that's trivial. So that's a good. Oh, well, come on. Okay, so we have good examples to look at from other. We are with fast radio bursts, kind of where gamma ray bursts were a few decades ago. Gamma ray bursts were another example where gamma ray telescopes were launched in the 1960s. They weren't gamma ray telescopes. They were launched initially. The Vela satellites were launched by the U.S. It was during the Cold War. And they were investigating whether or not Russians were trying to detonate nuclear bombs on the far side of the moon. That's how crazy things were at the time. But when they did launch, they found these gamma ray bursts, and they realized they were not the signature of a detonated nuclear bomb, something different. And for the following 25 years, there was a huge debate about where they came from. And it wasn't until, once again, we knew they were happening in some direction in the sky, but not good enough to localize to where they were happening. Some theories were that they were colliding asteroids nearby in our own solar system. Other theories were that they were huge energetic explosions of stars, or colliding neutron stars. Lots of theories again. Not quite 41, but definitely more than 10. And it wasn't until we actually saw them and localized them that we figured out what they were. Because there was two populations. They're the long ones. They typically last longer than 2 seconds, and the short ones. They're typically less than 2 seconds. The long ones. Eventually, and actually a lot of the work was led here at Caltech, what they would do is they'd get a detection from one of these satellites, and that satellite would send an alert down to the ground. And this was kind of like in the mid-1990s, and all the astronomers who worked in the field would have a mobile phone. And believe me, this was at a time when nobody else had mobile phones. And they'd get a text message saying, there's been a gamma ray burst. And they'd all race their telescopes and point their telescope to see if they could get a flash in that direction. And eventually they did. There was a flash of optical light and a flash of radio light, not just gamma rays. And it turns out when they got the optical light, they were able to localize it to a galaxy, and that galaxy happened to be a very small, very high star formation galaxy. And when they analyzed the light of the actual optical flash, it was the same light of a very particular type of supernova. And they saw that again and again and again. that you have a very particular type of supernova that happened to occur with long gamma ray bursts. And that's how it was figured out. What was happening was really giant stars were exploding, producing two jets when a black hole forms, and those jets were the gamma ray burst. Now, for the short bursts, there was never any. We were able to find the host galaxy, but never find the actual supernova. So the host galaxies were very different to the host galaxies of the long gamma ray bursts. They're much older, bigger galaxies typically. And instead of being on the bright part of the galaxy, these bursts were typically off the galaxy. And that meant that there was a different kind of population. You have to ask, what kind of explosion happens outside a galaxy rather than inside a galaxy? And one good example is when two neutron stars merge. What typically happens is you have to have two giant stars. One explodes, gives you a neutron star. The other explodes, gives you a neutron star. And through gravitational waves, they get closer and closer and they merge. Now, when they explode, they give a kick, a velocity kick, and the binary starts traveling out. And it takes 1 billion years for it to merge, and suddenly it's outside the galaxies. And that's why astronomers were theorizing, well, maybe that's what we're seeing. It was based on circumstantial evidence. It wasn't, in fact, until the last year, on up close, that in fact, it's only this week, there's a paper submitted to Nature that confirms they are, in fact, the cause of short gamma ray bursts. So we're using circumstantial evidence in that scenario. And with the same thing for fast radio bursts, we know a lot about galaxies and what happens in galaxies, and we can kind of piece together clues by looking at where they're coming from.
Questions?
You don't have to only ask about explosions, but if there's any random astronomy questions that you're curious about, ask away.
And we also have about 20 minutes left if you want to see the telescopes outside.
Well, you say that you work on different types of explosions. Could you just tell us a little bit about the different types of explosions that you're examining from radio telescopes?
Yeah. So I'm working on a project that is going to image the entire sky in the radio once every 2 years, 3 times. So over the next 6 years or so. And so what we're looking for are just things that have changed in the sky. What has appeared that did not exist 2 years ago, or did not exist in a historical radio survey that was from the 90s, right? And so the kinds of things that we're finding typically last for much longer than fast radio bursts, because you had to be super lucky. You had to be looking exactly in the right direction, exactly at that millisecond the fast radio burst went off in order to find one of those. But if you have an explosion that lasts for years, then it doesn't matter whether it was that 1 millisecond or another millisecond, right? You can see it. So the actual kinds of explosions that we're looking for are, for example, the afterglows of gamma ray bursts, which Gregg was just talking about. We're also looking for sort of lower velocity explosions of stars, ordinary supernovae. It turns out that a population that we may be seeing is these kinds of supernovae where in the last years of a star's life, it ejects off giant shells of its atmosphere. And after the star itself explodes, the extremely high velocity stuff that was ejected from the star slams right into the gas that it ejected right before it died. And that produces sort of a lingering afterglow that lasts for many years. In fact, I was just looking at a paper today that was talking about a supernova from the 1950s, I think like 1957, that we can still see the supernova, and it's still glowing. Yeah, so these are the kinds of explosions that I'm looking at. Other examples are what are called tidal disruption events. I'm not personally working on them, but we'll probably find a few. And those are where a star gets a little bit too close to a supermassive black hole. And the tidal forces from that black hole actually just rip the star apart. When it gets close, actually the star sort of flattens like a pancake, and then it rebounds. And then about half the material gets shredded and just ejected from the system entirely, and about half the material falls right into the black hole. And that material that's falling into the black hole is extremely hot, and it gives off light. And sometimes, in a few percent of the cases, for reasons we don't understand, you get these jets, just like you see in gamma ray bursts, and that's what we would see in the radio, for example. Yeah, and there's a whole zoo of explosions out there. Studying astronomical explosions is a super young science, and we're finding examples of really cool things all the time.
Yeah, I think there's some more interesting things to add to that. So you might ask, okay, there are all of these cool explosions out there, but why do we want to study them? Like, okay, you find an interesting explosion, you try to understand what produced it, but at the end of the day, you want to ask the question, why do we want to understand these explosions? And there are several reasons for why we want to do that. First of all, we know that the universe, when it started, which was about 13 billion years ago, the universe contained only hydrogen. There was nothing else. Some hydrogen, a bit of helium, and there was nothing else in the universe. But look around you today. Today we have such a wide diversity of elements, atoms. There is iron in our blood, calcium in our bones. There is all kinds of elements that did not exist in the universe when it was first created. So the natural question is, where did these elements form, and when did these form? It turns out that it's exactly explosions like these that formed all of these unique elements that we see around us today. So, for example, the example that Dylan was talking about, which is these massive ejections of material. We now today believe that that massive ejections like these from massive stars are the things that enriched the galaxies with all kinds of new elements, because it turns out that it is these stars that actually converted all of the hydrogen. They burned it to helium, they burned it helium to carbon, to oxygen, to silicon, and up to iron, all the stuff that we see around us today. And it is precisely these violent explosions that were able to transfer all of these material, all of these newly synthesized elements that were originally inside the cores of hot stars. So originally all this stuff was inside the core of a massive star. Like all of the iron in your body was inside the core of a massive star or inside some weird white dwarf. And all of these explosions were responsible for ejecting all of this material back into the interstellar medium, and all of this material then eventually coalesced into forming planets like the Earth, and we were all formed on Earth, so that's why we inherit all of this material. So at the end of the day, all of the stuff in your body was actually formed inside these explosions that we study today.
You have supernova in your blood, basically, is what he's saying.
Are you saying tidal disruptions might have distributed more of these elements than in supernova, or just played a larger role?
No, so I was talking about supernovae, yes. But for tidal disruption events, I think tidal disruption events aren't as much responsible for. Number one, they're not as common as supernovae. Supernovae are super common in the sense that if you go out and get a telescope and look at the sky, you will find a supernova tonight. They're so common. Tidal disruption events, not so much, and they're not as much responsible for producing these new elements as these massive stars. These massive stars produce tons and tons of new calcium, oxygen, magnesium, all of the stuff that we see around us today. But tidal disruption events are important for other reasons, including things like how they regulate things like star formation in galaxies, and how they control the growth of galaxies, and so on. So, yeah. Yep.
Are we seeing any of these explosions that are first-generation stars, or are they not at all common?
That's a really good question. So, turns out that most massive stars, so the most massive stars also have the shortest lifetimes, in the sense that the more massive a star is, the faster it uses up its nuclear fuel. So all stars are originally born with hydrogen. At least, even even the first stars would actually have almost pure hydrogen and some helium. So they use up their fuel really fast. So the more massive a star is, the shorter is its lifetime. So in that sense, the first generation of stars that were formed in the universe, they're long gone. But there are these unique explosions. These are known as superluminous supernovae. I know it's kind of a weird name because you already have a super and you add one more super to it. Yes. So it turns out that superluminous supernovae are the brightest of supernovae that we know of. And they are typically a factor of 100 to 1,000 times brighter than the normal population of supernovae. And what that means is that if you have a supernova that is much, much brighter than the standard population, you can also see it out to much further distances. Because the flux from any source always falls down with distance. So if you have something that is much brighter than the typical population, you also see it out to much further distances. So it turns out that it's these superluminous supernovae that allow us to trace stars that were formed much earlier in the universe than any of the stars we see nearby. And I mean, I'm talking about ages where I think where the universe was as young as I think 1 billion or 2 billion years old. You can see far back in time. So when you see a superluminous supernova that is really far out, it also means that you're also looking really far back in the history of the universe. So some of these superluminous supernovae are bright enough so that you can actually see stars. There is no other way to do this, by the way. There is no other way to even see the galaxies out to the distance because the galaxies are not bright enough. They're really small. It is these superluminous supernovae that you can see out to distances of, far enough to actually see what was happening in the universe a few 100 million years after they were formed. And that's even true for gamma ray bursts. Gamma ray bursts are so luminous, I think the most luminous gamma ray burst, the furthest gamma ray burst ever observed, that thing happened like a few 100 million years after the Big Bang. So, these are really powerful probes of what the universe was doing in terms of star formation really early after it formed.
And that was almost certainly the exact kind of star you described, like a star that was mostly just hydrogen before. So yeah, we do see those gamma ray bursts we see from the edge of the universe are exactly those kind of stars.
Yep.
You mentioned in your talk that we haven't observed this supernova in our own galaxy. Did you say 5 or 6 decades?
Well, we haven't seen directly for much longer than that, but we could infer that, because the big issue is a lot of the light from the supernovas in our galaxy, it's actually easier for us to see supernova in other galaxies than our galaxy a lot of the time, just because very often we're looking right along the disk where the light, and the dust blocks so much of the light. Now, if it happened today, we would see it, but, if it happened a century ago, we would not have seen it. And we do think there are remnants that are about a century old. The last bright one we've seen, where it was like a nova stella, a new star in the sky, is around the time of Tycho Brahe, more like 500-600 years ago. That was the last one that was brighter than Venus, for example, in the night sky. And that's how bright they get. They become incredibly bright in the night sky where they happen in our own galaxy and are not blocked by dust.
And if one happened now, what would be the types of information we gain from seeing it now?
Be hugely important. First thing we'd see would be a burst of neutrinos, and that would give us some very fundamental understanding of the actual processes that are happening inside the very core of the supernova itself. We still, we try to explode stars in simulations. We try to add the ingredients to do that, and we still can't do that very well at all. So there's lots of information we will learn by looking at neutrinos, by looking at where most of the energy actually is. 99% of the energy in the explosion is just in pure neutrinos. Looking at the shape, morphology of a young supernova. Looking for the remnant very early on. The last time we could do this wasn't actually in our galaxy, but it was very nearby. There was a supernova in the Large Magellanic Cloud that was detected in 1987. And that was a spectacular event. And we detected neutrinos from that event, actually. And we're still watching the explosion to this day. And we still have not seen the pulsar, if it exists. So that's, there are still papers. There was one this week that was still looking for the pulsar 31 years later. There have been claims that it's been detected, and they've been proven to be false. So yeah, we would learn a lot. It would also be a big pain for people who do X-ray and radio astronomy, because suddenly you'd have like something that would be literally brighter than the sun showing up somewhere over here. And makes it very difficult.
Just to add on to what Greg was saying about the explosion in one of the Milky Way satellite galaxies in 1987, one of the big mysteries is, do we get these molecules that astronomers call dust from these sorts of explosions? Because, as we were saying earlier, we see these gamma ray bursts from extremely far away when the universe was maybe a few hundred million years old, and yet we still see dust in that's absorbing some of the light from those gamma ray bursts. And so the question is, what can produce dust at such an early age? And it's thought that the only thing that can happen on timescales that are fast enough is supernovae. But we've never actually directly detected dust being formed in these supernovae. And so one of the questions that we might be able to answer in the next few years from this very explosion, supernova 1987A, is whether the dust that was produced in the cooling remnants of the supernova will survive when what's called a reverse shock passes through the dust that was ejected out. Yeah, so stay tuned. Still a lot of things we're learning from this one explosion that happened really close by.
Mexican standoff here, I think.
Well, it's still explosion-related question. I was looking at M57 at Griffin, and so one question I had came to mind was like, so this is probably still exploding, even though it looks like it's frozen. Like, how fast is it currently moving apart? Is there any way to figure that out? Like the speed at which
Yeah, we actually, so the Crab Nebula, I showed the Crab Nebula there in my talk. If you take an image from 20 years ago of the Crab Nebula and put it overlay it, it's actually bigger now than it was 20 years ago, and substantially bigger than it was a century ago. So right now it's expanding at about 1,500 kilometers per second. We know when it exploded, initially it was expanding about 10,000 kilometers per second. But that was first noted in the 1920s. Hubble actually did the blinking to see, somebody else actually discovered that it was changing. And he did the kind of winding back of the clock to see when the explosion would have when the nebula would have been basically a single entity. And they realized it was due to a very famous nova stella that was seen in China almost 1,000 years ago. 1054 AD, and even in New Mexico, there's drawings on caves in New Mexico that show that same event, and they were able to figure out that it was that based on the location of the moon relative to the drawing of the supernova. So it would have been like brighter than Venus for like some period of time, and there's historical records of that being somewhere in Taurus where the Crab Nebula is, and that was a massive step in understanding what supernova are, and piecing together what these nebula are actually also, these remnants.
So the Crab Nebula in the last 20 years expanded about 15,000 kilometers
per second. 1,500 kilometers per second. Yeah, it's very large. It's like light years across, but you can still see it over time. It's really cool. The videos you can look on YouTube are pretty cool.
When detecting some of these radio bursts, are any of them blocked when you try to look through them? Like if one of them is in the line of sight for a black hole, is it blocked? Is it completely blocked?
So if in that particular case, if you had a black hole in between, it would be lensed around the black hole, so you'd still see it. Yeah, but and radio waves in general can travel through almost anything. Not anything, but almost anything. If you had a very dense plasma, let's say that the FRBs are coming from a young supernova, they may get absorbed by the surrounding gas. But that being for anything.
We have time for one more question.
Yep. Okay. Yeah. Yeah. That's actually very common when you look at nearby dwarf galaxies. So the idea is, one of the questions that is still a question in astronomy is, what was the composition of the universe after the universe was formed? So we know that there was a lot of hydrogen, some helium, and we know that there was some deuterium as well. So the way to determine how much deuterium was there in the originally in the universe is to go and look at these very small nearby dwarf galaxies, because those are the galaxies where there's not been a much of star formation. All of the stars are really old. So the gas that you're looking at, most of that gas is very pristine gas from what the universe was. So you can go and take a spectrum of that galaxy.